All right, let's get started. So we've been talking about inheritance and overrides and your superclass constructors. Don't forget your superclass constructor calls. And I haven't done this in a while, so let's just give a quick status of where we're at in the course. We have the Test 2 final deadline. This doesn't apply to very many of you, but Test 2 final deadline is coming up. I'm glad that I don't have to talk about that much. It only applies to a few of you, and of those few, most of them already failed, so it doesn't really affect many people at all. But Test 3 late deadline, make sure we're hitting these ones. Once we hit the Test 3 final deadline, that is, at least in my opinion, one of the tougher checkpoints of the course, maybe the way to say it. Test 3, most of you have started the test. You're well into it right now. That's a pretty good jump up in difficulty from Test 1 and 2. Test 1 and 2 is a pretty easy transition into the course, into 116, getting used to Java, getting used to testing, what's the Autolab feedback going to look like, all that kind of stuff. And Test 3 is where probably the first real coding challenge. How do you remove a reviewer from a rating from a linked list by reviewer ID in multiple objects? You have to get the reviewer ID from the object. It's not too much, but then trying to figure out exactly how to manipulate the references of the linked list, especially when it can either be the first node, the last node, or anything in between, kind of three separate cases. So a decent amount going on. And then Task 4 steps it up a little bit as well. So Task 4, almost by design. Task 4, you do have an extra week if you want to use spring break to start to work on that Task 4. But Test 3 and 4 is where things step up a little bit, at least in my opinion. I think that's pretty objective, though. And then once you get through Test 3 and 4, because we're about to hit the stage where you're all going through Tests 3 and 4, once you get through Test 3 and 4, I think, and data kind of supports this, once you get through Test 3 and 4, you're most likely going to make it the whole way. Once you make it through that last hurdle, there's not another... Again, in my opinion, this one might be a little more subjective. I don't think there's another jump up in difficulty like there is from 2 to 3. Like 2 to 3 is a pretty big jump. 3 to 4 is a small jump up. But from 4 to 5, 6, 7, 8, there's not another big jump up in difficulty. The difficulty kind of levels off after 4. So just every once in a while, I like to talk about where we're at in the course. It's kind of where we're at. Make it through Task 4. You got what it takes to make it the rest of the way. Okay, with that, we got a lot of slides today. Let's talk about them. That's all 312 questions. Let's go. So comparators. We talked about what inheritance is. Inheritance, your superclass constructor calls, the inheriting state and behavior, and then overrides. Let's apply this to an actual application. Right now you have everything you need to know about inheritance. You can do all of the homework. Well, I mean, some of the homework does ask you to do some comparator stuff, but it's not a new concept. The comparator, you're going to extend a class and then override one method. So you already know the concept that we need for comparators. But let's talk about comparators as a use case of inheritance. So let's do this. Oh, I'm not even on Big Mouse. Okay. So the problem that we have, and you've seen this a little bit in oh, no, you don't anymore. I was going to say in 115, but no, you kind of don't see this anymore. I had to change the way I talk about this because I can't rely on that. Well, I couldn't anyway. But anyway, so here's the problem. We need to compare two values. In 115, you do sort and then key equals, and then sorts on a specific key. So it's a little bit different these days than the way we used to do it. But comparator, we need to compare two values. That's all we want to do is compare two values with our comparator. Between these two values, which one comes before the other one? That's the only question that we're answering with comparators. But this is the problem that we have. This is the problem we want to solve. How do we compare two values in some sorted order? And we're going to use a comparator for that. So comparator, there's two styles of this. The Boolean one, this is the one we'll use in the course for most of our applications. But I want to talk about this other style. Before, I could say this is what you've seen in 115. You don't see it in 115 anymore, but it is the style of Java's built-in comparators, so it still does come up. When you call a built-in compare method, compare to, or compare with, I forget what it's called, or compare with, ignore case, or something like that. For the homework so far, you just use equals, ignore case, so it hasn't come up yet, but this can come up later in the future, foreshadowing, that we might use this style also. So the first style returns an int, and that int is negative if the first input, the first argument you give it, comes before the second one, and positive integer if the second one comes before the first, and 0 if their order is tied. That's the style that if you use any of built-in Java compare methods, this is what it's going to give you, is an integer, positive, negative, or 0, so 3 different types of output that it can give you. And the one we'll build in the course, it returns a Boolean, so only 2 pieces of information it can give us, 2 different outcomes. Either it's true if the first input comes before the second one, or false otherwise. So if it's a tie, it's going to return false. If the second one comes before the first one, it's going to return false. So 2 of those modes got combined into false, which is actually just as powerful as this one, as it turns out, because you can swap the order of the inputs, and we'll talk about that when the time comes. But we can swap the order of the inputs to figure out if it's a tie or not. So the comparator that returns 2 ints, including compare to, that's what it was, including Java's built-in compare methods, if you ever use these, which it will come up in one of the homeworks. I forget off the top of my head, but it does come up at one point. It comes up in this homework. Yeah, in homework 4, writing the compare methods. Yeah, it comes up soon. You'll call compare to ignore case, case matters. Oh my goodness. I just don't want to say something wrong. I think we ignore case for that one. Maybe we don't, though. No, because it's the song title comparator. We don't ignore case in that one. You just call compare to. But it's going to return something like this. When you call Java's compare to method, it's going to return a -1 if the first argument comes before the second one. And the first argument is in this. It's in the keyword this, so it's a little different than 2 arguments. But I still see this as 2 arguments. You have this and the other one. If this comes before the other one, then it returns -1. If this comes after the other one, it'll return 1. And if they're tied, it'll return 0. Now, this is common for a compare method to return -1, 1, and 0. But the spec says a positive integer, a negative integer, or 0. So do not, feel like I see this bug at least once every semester, do not in your code say if compare to returns -1, then this must be the case. This must come before the other, before the argument. Don't do that. Always check, is it less than 0? If it's less than 0, 0, or greater than 0, those are the checks you want to make. A lot of implementations will use 1 and -1, but not always. And when you have a method that doesn't do 1 and -1, and you have code that checks if it's equal to 1, then it's not hitting any of your cases if it returns like -5. It's still following the spec. It's a number less than 0, but it might break your code. So always check, is it less than 0, is it greater than 0, or is it 0? So that's the Java style of comparators. And if we're checking strings, the compare to will check in this very specific order. It'll check them alphabetically with, well, not quite alphabetically. They're alphabetical, but how do I word this? Capital letters, every single capital letter will come before every single lowercase letter. So we won't get exactly the ordering that we want all the time if we're not ignoring case. This is why in the homework we want to ignore case when we're doing our comparisons. Is that if we're not ignoring case, anything that's capitalized is coming before anything that starts with a lowercase. That's not what we want. We don't want something that starts with a capital Z coming before something that comes with a lowercase a, in most cases anyway. Okay, so that's why we do ignore case. That's going to get rid of these issues for us because this will compare based on their ASCII values. If you want to think about ASCII, the ASCII capital letters come before the lowercase letters, so that's why it does that. And this lines up exactly with the spec for the homework. The way that we compare our strings with the title comparator, it's going to be exactly what Java does. So I have all those specific things in there. I'm basically saying use the compare to method that's built into Java. Okay, our Boolean one that we'll use, this is the one that we'll write for our comparators, is going to return a Boolean. True if the first parameter comes before the second one, and we will have two parameters. We're not going to use this, the keyword this, and false otherwise, including ties. Let's write one of these things. We have this comparator. We're going to write a compare method. It takes two ints. Very simple comparator. We want two ints, and we want to sort in decreasing order. The default, if we tell Java to sort a list of ints, it's going to sort in increasing order. That's just the default sorting for any numbers. You want them to start at the lowest one and then go up. So if we want to do some custom sorting, we're going to do the craziest thing. Whoa, we want to sort in decreasing order. Almost the same exact thing, but just enough as a proof of concept that we can sort by anything that we think of. If we want to sort by absolute value or the distance the number has from 100, whatever we want to sort by, we can sort these things by them. Proof of concept, we're going to sort in decreasing order. So we're going to return A greater than B. So if A comes before B in this sorted order, that would mean that A would have to be greater than B. And that's exactly what we're going to return. A greater than B, and return this. This resolves to a Boolean, either true or false, and we're just going to return that. So if A is greater than B, return true. The first argument comes before the second one. And if they're equal to each other, notice I'm not using greater than or equal. I'm using strictly greater than. So it'll be false if they're equal and false if B is larger than A. That gives me all of the properties that I would need from this comparator to be able to sort in decreasing order. The default sorting for ints is just the less than operator. If we use the less than operator here, we get that default ordering, that default sorting. Okay, and we want to use classes here because we're going to use inheritance for reasons. So with this class, or with this method, we're going to wrap it in a class because everything has to be in a class. I guess that's the reason. But we're going to eventually extend comparator so we can do some inheritance. But we're going to wrap this up in a class. And there's no constructor. This already came up a few times in lecture, so it's less important now. This is where it's designed to come into play in lecture. But we had some good questions and talked about it. This class gets the default constructor. I'm not specifying any constructor, so it automatically gets the default constructor that takes no parameters and does nothing. So this is the same exact code. This is the default constructor explicitly stated. This is implicit. It's not explicitly anywhere in my code, but this is the same exact code. This class and this class, the default constructor takes no parameters and has no code in the body. That's what we get if we don't specify a constructor. So that constructor is always there. Every single class has a constructor. If you specify one, you get whatever you specify. If you don't, you get yourself the default constructor. And that default constructor, in the context of inheritance, that default constructor is still called even if no constructors are explicit. The superconstructor is still called even if it's the default constructor. It'll just be a stack frame with this and then a reference to the object being created. But it is still there. It still does get its own stack frame. Okay, now we can talk about comparators. So comparators, well, we have been talking about comparators, but the comparator class, so we can do some inheritance since it's inheritance week, we're going to create a comparator class that takes a type parameter so it can compare anything that we want, any type that we want using this comparator. And we're going to extend this and specify the type parameter when we extend the class. So we're going to create a comparator of a specific type whenever we create a comparator class. So this comparator, this int decreasing comparator, is going to extend comparator of integers. So this comparator is made to compare two integers. The compare method in the comparator class, the one that we're going to override, takes two values of the type parameter type. So when I override the compare method, I have to give it the same type that I gave when I extended this class, when I inherited from this class. So we can use type parameters in inheritance as well as in just classes in general. And then since we're using generics, that's the only time I'm going to ever use capital I integer is when we have generics. We have generics now, so our ints become integer, including here because it is the type parameter. Unless I'm forced to, I will never use the capital I integer. I still see that pretty regularly in office hours. What does this error mean when it says method signature not found and there's a capital D double in there? I'm like, well, I said this like 100 times in lecture. How are you still coming to me with this? I always assume they're Paul's students. I should ask, actually. I don't know if Paul said that 100 times in lecture. So, all right. So this is our inheritance, and then we can extend comparator of t. The advantage of doing this is we can extend comparator of t with any type and write any compare method. What we're building up to is being able to use these comparators to sort any type in any way. We have 100% complete flexibility in the way we use these comparators. That's what we're after. And we won't fully get that until next Wednesday when we talk about binary search trees. Then we're going to use comparators and have that tree sort anything in any way. Gives us full flexibility, full power in how we sort anything that we want. Yes, we're just doing int decreasing here, but this is just a proof of concept. Bless you. Okay, and this is, when I say stubbed out, I say this in the homework documents fairly often. You can write the methods and stub them out, but the methods have to exist. This is what I mean is we're just going to have some default return value, just return false here. If this method returned an int, I would do return 0. If it returned a string, I would do return empty string. Just something so the method compiles. That's all I have here is just a method that will compile. And I return a default value of false, so I'm always saying this is either a tie or the second one comes before the first one. It doesn't make sense, and this method should never actually be called because it doesn't do anything. It just returns false. It's made only to be overridden, and we're going to override it and give it some actual functionality. For those of you who want some more foreshadowing, this will eventually, when we talk about polymorphism and add in the rest of the inheritance content, this will eventually be an abstract method, and this will become an interface. But we're not talking about that quite yet, so I'll just leave it as a foreshadow for now. But we will get rid of this return false. We will get rid of this in polymorphism week, and we'll revisit this example and update the code. We're only talking about classes. We're not doing abstract classes or interfaces yet, but we will get there. For those of you who know what that is, don't worry, it's coming, just not this week. In 4 weeks, we'll talk about that. Okay, and with this comparator, we do have a lot of flexibility, so let's use a little bit of that. Let's flex that and see what we could do with this and show something a little more interesting that we might do. So first of all, these classes are, well, classes. We can use any state and behavior we want to add to this. We have to have a compare method. We have to override the compare method, or I guess we don't technically have to yet, but we should because we don't want to just return false. We want to actually sort based on something. So this has to be here. But we can also add whatever else we want. Here I'm adding a helper method to be able to help how I'm actually sorting. I can have helper methods. I can have named constants. I can have instance variables if I want. I can do whatever I want here. So here I have a helper method that's going to compute distance for me. And I want to sort game items based on their distance from the origin. So I'm going to sort using less than, so this will be an increasing order, but the values that I'm sorting by are the distance to the origin. I guess I don't have -0 here because it'd be pointless, but the distance to the origin, the square root of the sum of the squares, that's going to give me distance from the origin of the game, and sort based on those values, which is something we might want to do at some point. And we can expand this. Not in the slides, but I want to talk about it. We can add a constructor here. Maybe we want to Maybe we want to sort by something more dynamic or more useful, depending on how you look at it, and sort by the distance these items have to the player object, I guess, but the player character. Then I can have distance from player, have a constructor that takes an object of type player, and then the helper method is going to compute the distance between that object and the player, and then this would do the same thing called the helper method. And now even as the player moves, I can sort based on that comparator again to be able to always have a list of all of the items in the game sorted by their distance to the player, which is a more interesting thing, something we might really want to do. Distance to the origin probably doesn't make sense in a lot of contexts, but distance from the player, that's something we're going to want. Like, that's something that's going to come up. Even if we're just trying to figure out like which objects should have the highest priority for rendering, which one should have the most GPU power assigned to them. Well, it's the ones that are closer to the player because the player's seen them larger, seen the models up close. So a lot of things we want. Or to highlight them, show the player like what objects they can interact with. I don't want to highlight that object way over there. I want the objects that are close to the player. Maybe the 5 closest objects within a certain threshold. I'm going to want to sort those objects based on the distance to that player. When overriding a method, do you keep the same method structure but switch out the parameter types? Bless you. In this case, yeah, because the parameter types are a generic type, I'm not actually changing the parameter types, but I am specifying what the type is, what the type parameter is in these overrides. So what I could do is say extends comparator. Oh, that's a bad example. I can take a type parameter here and say extends comparator of t, and then have these still be a generic type t and leave it up to somebody else to specify the type. Like, I could do something like that, but the way I'm using the comparator is I'm extending the comparator and then specifying what t is in this class. In the distance from origin class, t is game item. So wherever t comes up, including the method that I'm overriding, t has to be game item because it has to match the type parameter. In int decreasing, I said integer. So integer has to be integer right here. So the signature has to be identical to the inherited method, but that inherited method used the type parameter, so I do get a little more flexibility with the methods that I'm overriding. It has to match the type parameter in this case, integer here, game item here. So the type does change in this case, but the type was a type parameter. In general, the parameter types will not change, but it's just a unique case here with a type parameter. Okay, any other questions on this? Okay. I have a question for you. How the hell do we sort with this? We have this comparator, but it only compares 2 things. How do I use a comparator that compares 2 things and use it to sort a data structure that can have any number of elements in it? I might have a data structure with 1,000,000 elements, and you gave me a comparator that takes 2 things and returns true or false. How am I going to use that to actually sort? So let's talk about that. Let's go through an insertion sort example, which I think is still the sorting method they do in 115. Either insertion or selection sort. I'm going to do insertion sort, though. Insertion sort is going to create an empty output array and go through each element in the input and figure out where it should go in the output. So we're going to go through 1, 6, 5 and insert them in the correct position in the output. That's what our insertion sorting algorithm does. It's one of our O of n squared sorting algorithms, which means it's slow, but it's simple and it's easy to use for a lecture example like this. Okay, and I only use 3 elements because we got a memory diagram coming up, and with more than 3, it just gets painful going through it all. Okay, so for the first one, there's no decision to make. The first element in the input is just going to be copied to the output in index 0. There's no other choice. There's no other place for it to go. We have an empty data structure, and we're adding the first element to it. It's just the only element. Easy day. Okay, and then when we get to 6, we have to start doing some work. This is where our comparator is going to come into play. So our comparator, we're going to take 6 and ask where it needs to be inserted, and we're going to compare 1 and 6 with our comparator. We're taking just two values and comparing two at a time. We're going to compare 1 and 6 and ask our comparator, does 1 come before 6? And our comparator is going to say false. Remember, this is the greater than comparator, so we're sorting in decreasing order. Does 1 come before 6? And once it returns false, we know where we're going to insert that value. So 6 is going to go in that first spot before 1, and then 1 is going to get shoved down the line. For 5, we're going to check, does 6 come before 5? And the comparator says true. If the comparator says true, we're going to move down the line until it says false, and that's going to be the place where we insert this value. So for 6, it says false. We move down to 1. Back when the array looked like this, it'll say false. Does 6 come before 5? False. Move on. Does 1 come before 5? True. Does 6 come before 5? True. Does 1 come before 5? False. Once it returns false, that's the position that we insert. So at index 1, that's where we're going to insert our 5, and then 1 gets pushed down to index 2. So that's our algorithm. We keep asking our comparator until it returns false, and that's where we insert. And when I show you the code's going to word that a little bit differently. It's going to count the number of times the comparator returned true, and that's going to be the place to insert. So when I'm inserting 5, I'm going to say, does 6 come before 5? True. Does 1 come before 5? False. So I got 1 true, so I'll insert at index 1. Will be our algorithm. And when we go through this, we're only asking the comparator 2 values at a time, and we're able to sort any number of values. And here's the code. I'm going to hit you with all the code here. So our code is first going to take a comparator. We're going to write a sorting method, a sorting algorithm. It's going to be a method in a class, this sort method. And we're going to write this in a class that takes a type parameter and a comparator of that type. This is what gives us the biggest flexibility that we want. Because what we want here, if we're writing our goals to write a sorting algorithm, we're sitting down and we're like, okay, we're going to write a sorting algorithm. If I'm going to sit down and write that sorting algorithm, what I don't want to do is ever do that again. I want to write one sorting algorithm that's going to sort anything in any order ever and then be done with it. Wrap that up, test it, ship it. That's our one sorting algorithm. And this is what happens in languages, in Java, Python, whatever. They'll have one sorting algorithm, and that algorithm is designed to sort anything in any way, even classes that they've never heard of, classes that you wrote, the game item, the player class. It can sort those things because it works on comparators. You tell it how to sort the thing you gave it, and it'll run the algorithm based on that comparator. So we're going to take a comparator and a type parameter, a comparator that can sort that. We're going to store the comparator in an instance variable so we can call it later and assign that instance variable in the constructor. So we're getting a comparator and specifying the type parameter, and then we would say like new sorter of integer and give the constructor an int decreasing comparator. Then we can reuse this any type, any comparator, it's going to be able to sort it. That's what we want. Then we're going to call the sort method, which is going to take an array list of the type parameter and return a new array list of that type parameter, but with all the same values, but in sorted order. That's what we want. Whenever we have this, we have to be careful. I've said this a lot of times this semester, but hopefully I can get this point to stick. You're getting a reference to an array list. Whenever you get a reference, somebody hands you a reference to their array list, or you somewhere else in your code, you have to be careful with what you do with that reference. You don't want to go over to the heap and change the instance variables. You don't want to mess with the instance variables of this thing. So the first thing we're going to do is create a new array list for the output, and we're never going to modify the input array list at all. Once you start modifying your inputs that were given to you by references, that's a really good way to get some bugs that are not going to be super easy to debug. Those ones are going to be kind of tricky to find. You might not even see the bug for quite a while until the code is in your user's hands and they see the bug. You don't want to mess with these things. Don't go over to the heap unless that's specifically what the method is supposed to do. do not go over to the heap and make changes to the inputs. So we're creating a new output, and then we'll add all the values to the output. And then the sorting algorithm itself. So this is where we're going to go through all of the values of the input list and figure out where they should go in the output list. So we're going to initialize our location to 0, go through all of the values in the output list, call the comparator, and count how many times the comparator returned true. And then once we have how many times it returned true, we're going to add to the output at that location the value that we're inserting. The add method can take two parameters if you give it two arguments. If you give it two arguments, the first one is the index where you want to insert this thing, and the second thing is the thing that you want to insert. If you give it one argument, it's going to add at the end of the array list. That's the default behavior. If you want to insert anywhere else in the array list, you can give it the index where you want to insert. So for example, if this is the very first thing that we're inserting, location is 0, this loop does nothing, and then we insert it at index 0, the value that we're inserting. So once we go through that loop, we'll have everything in the output array list, exactly where it's supposed to be. And then we'll return that thing. We'll return it and give it to whoever called this, which is from our main method in this example. So to initialize this, we're going to create a new sorter object with a comparator, and we have a bit of an issue here. We're calling new sorter with a new int decreasing. We're giving this an object of type int decreasing, but the constructor takes a comparator of t. It wants an object of type, or a reference to an object of type comparator of t. So it looks like we have a big issue here, and it's actually not an issue. I've been saying since the beginning of the semester, your object, Java is strongly typed. If you have a variable of one type, it can only ever store values of that type. If you have a method that takes a type, it has to take objects of that type or values of that type. If it returns a type, it has to return exactly that type. And now I'm showing you code that doesn't do that, doesn't follow that at all. So for now, I'll just say that this is allowed. This code compiles, it runs, everything's fine. And the reason this works is through polymorphism, so we'll have a lot more details in polymorphism week. And the reason specifically that this works is because int decreasing extends comparator. So int decreasing gets all of the state and behavior of comparator, but it's actually a little stronger than that. Int decreasing actually is of type comparator. It inherits the whole type itself, too. So wherever I need a comparator, I can actually provide int decreasing. I can provide song title comparator, song Bayesian average comparator. I can provide all those comparators wherever something takes a comparator, as long as the type parameter matches. So my sorter of integer takes a comparator of integer. Since int decreasing extends comparator of integer, this code is valid and everything works fine. So that's the quick explanation. But again, I do a lot of selling of polymorphism week and during inheritance week. We'll talk about more of it when we get to polymorphism. Yeah, for now, it's allowed. And we need to do this to talk about BSTs next week, so we do have to do a little bit of polymorphism before we get to that week. But for now, that is allowed. Everything's fine with that. Okay, memory diagram. Let's go through this and talk about exactly how it works in memory. Again, I'm going back to my slide memory diagrams because I'll never get through a memory diagram using the tracing tool. I don't know how Paul does it, but I can't get through one. So I'm going to rely on my slides so we can actually get through the content. So this starts with this kind of beast of a line. This line has quite a bit going on. So let's go through this one step at a time because right from line 1, I got a lot going on. This is, I guess, mostly review. I guess one of these things I didn't really talk about. We never called a method inside the argument list of another method before. I think that one's new. But let's talk about how this works. So whenever we call a method, what has to happen is all of the arguments need to be resolved first. They need to be resolved down to their values, and then we can call the method that we're calling. Now, usually this isn't a big case. We'll have like int literals. Resolving an int literal, it's just its literal value. Or a variable. A variable resolves to its value. It's just a quick table lookup from the stack. But this time it's a method call, so we have to think about it a little bit more and make sure that we get our method calls in the right order. So this method call is going to happen first before the sorter method call. So the int decreasing constructor is the first thing on the stack, the first stack frame on the stack. And int decreasing, we're going to call its constructor, which doesn't exist, which means we get the default constructor. So we get the default constructor. The default constructor still, even though there's no constructor code here, still has to call the superclass constructor. Do not forget your superclass constructor calls. Calls the superclass constructor, which also only has the default constructor, and also there's no instance variables here. But these two constructor calls are still here, with this being a reference to the object that's being created, and we have an object with no instance variables. We still need that object on the heap. I don't think we'll do this on a quiz, but we still have that object on the heap with no instance variables. We'd probably just artificially stuff an instance variable in there on the quiz because it kind of looks weird having an empty object on the heap. It's a good indication that your classes are set up in a way that you should have used static methods. But you can't extend static methods, so I don't know, it kind of makes sense for comparators specifically. But anyway, we have an object on the heap with no instance variables. We have two constructor calls that don't exist in the code that only have this and then a reference. I guess that's an exception to the rule of thumb of if you don't see the code, then you don't have to trace it. If it's a default constructor, it should still be traced. But again, we shouldn't be throwing that at you on the quiz. Speaking of, I almost forgot to mention the whole two-string fiasco. I looked into the issue with that on the quiz, and unfortunately, I don't think there was an issue that calls for regrading or anything. The object that toString was being called on, it was a type parameter, which did make it a little trickier than maybe it should have been. But the type parameter was a string. So you were calling toString on a string. And the toString call was there to make it explicit that we're converting that to a string. But it was already a string. The string's toString method just returns itself. So you get the string value. It wasn't intended to be confusing. The intent was to make it more explicit by calling toString explicitly, but it ended up causing more confusion than it was supposed to. But since it was a string that toString was being called on, we didn't have to provide the code for that toString method, and you didn't have to trace the toString method either. I think that was part of the confusion too. You didn't have to trace it because it was the string's toString method. It was internal to Java. We never trace something that's internal to Java, so no tracing it, but you did have to know that toString on a string just returns the string, and that's what was being printed to the screen was the string's value. For the makeup quiz, we got rid of that. I said, can we not do that again? But I don't think it was atrocious enough. Like, it was clear enough that you should have been able to trace it still. It wasn't atrocious enough for a regrade. Okay. We got to get back on track. I'm glad I remembered to say that, though, because there was a big discussion last time. All right. So now that we have the int decreasing constructor returning, no return arrow because there's no variable it's returning to. Return arrows only if you're returning into a variable. And then the recursion things, if you mess up the recursion return arrows, though, like I said last time, I don't care. That is something you better come to me and say, hey, I lost credit because they said my recursion return arrows were messed up. I'm giving you credit for that, as long as everything else is correct. So now that this one returned, we have the arguments, all the arguments. There's only one here, but all the arguments are resolved. So we get to call the sorter constructor, get this thing on the stack. This does not extend anything explicitly. The object constructor technically does go on the stack. It does. The stack frame's there. It is called. That does happen. Internal to Java, so we don't trace it. We don't care about it. So we don't trace the object. Doesn't extend anything explicitly, so we're not going to trace any superclass constructor calls. And this does have parameters, instance variables, all the old stuff. We take a comparator, that's the int decreasing, whatever this constructor returned, which is OX350 in this example. This is a reference to the object being created. We get the comparator instance variable, set it equal to comparator from the stack frame, and we get all that goodness. You need to shut up. I usually have my phone silenced. I must have forgot today. But so we call that returns, and that does have a return arrow. Sorter is now, after all that, 3 constructor stack frames and 2 objects later, sorter gets OX321. 321. That bugs me a little bit. That I always say like 350 and stuff. These are hex values, so it's not technically 321. It's 321 to be correct, but I'm okay not being correct. All right, so we have new array list, the arrays.as list. This has to resolve first, and then the array list constructor resolves. But hey, guess what? That's all internal to Java, so who cares? We're just going to throw list on the stack with the value. And here, I get this question a bit because this is one of the big differences between doing these in the slides versus the tracing tool. The main stack frame, sorter, and list would both be at the top in the main stack frame. That's the big difference between these things, between the structure of them. This is how we used to do things before the tracing tool. Since you create sorter, you have these stack frames on there, and you can't exactly move these stack frames down. If you're pen and paper, you can't move these stack frames down to put list in there. We can do this in the tracing tool, so we switch things up and explicitly put the main stack frame in there. But since we couldn't do it with pen and paper, this is the way we used to do it. So that's the only reason why it's different. Anything not explicitly in a stack frame is in the main stack frame, the way I'm doing these in the slides. Okay, so all that's internal to Java. List gets whatever the result is, and I have this array list with the values that I got from asList, 165, and indexes 0, 1, 2. All that's old stuff. And then we're going to call the sort method. Here's where quite a bit of stuff is going on. I need a pretty big stack frame. And in the slides, I know exactly how much room I'll need, so I can make it as big as it needs to be. Input gets a reference to that array list that was created. We're going to create the output array list as an empty array list. We're going to start this loop. We're going to iterate over the values to insert. I'm using my enhanced for loop or my for each loop in Java. So value to insert is going to iterate over the values. So it starts at 1, and it'll go to 6 and 5. Location initialized to 0. And nothing happens. So the inner loop isn't executed at all in this case because output is empty. So we're iterating over all the values of output. That's a total of no values at all. So we never go into this loop at all. It's just completely skipped over. And then output.add location value to insert. So location 0, so at index 0, insert 1. So at index 0, we're going to insert 1 and start over back at the top. So we hit the end of the loop. We're going to go back to the top of this loop. Location is 0. And this is kind of a nuanced point, but location is technically a new variable because we're in a new block. It's redeclared. But we are going to pretend when a variable is redeclared, in this case, we are going to cross out the value and just write the new value. If that comes up on a quiz, it's another thing that we should just avoid on the quiz because it's too much of a nuanced point. But to save space, like we could cross out location and then write location again, but then it just takes up more space and it's just kind of, kind of gross. Plus we can't do that in the tracing tool anyway. So we just cross out the value and rewrite the value, even if it's being redeclared and not just reassigned. Okay. But technically a new variable was just created called location. All right. So location is 0, and this time we are actually going to hit the inner loop. So we have this inner loop, value to compare, iterating over output. It's going to get the value 1, the only value it's going to get. And inside this loop, we have a good bit of code going on here inside our conditional. This one, I want to trace this whole thing through. We're in this stack frame right now, the sort stack frame. We're doing this which is a reference to the sorter .comparator.compare. So this dot comparator dot compare, we're at an object of type int decreasing. So we're going to look in the int decreasing class for a compare method. We find this compare method, and this is the one that's going to be called. So remember our progression of how we find the methods. Start in the class matching the object type. If you find it, good. If you don't find it, move on to the superclass constructor, or to the superclass. We never get to the superclass, so we never get to this one because we have the overridden compare method right here. So this is the method we're going to call. This is a reference to int decreasing, the int decreasing object. That was the calling object. So this is a reference to that comparator. And then A and B are value to compare, value to insert, value to compare, value to insert. Does 1 come before 6 in this ordering? So 1 greater than 6 is going to be false. Don't know why I had to think about that one for a second. And when we created this stack frame, this came up earlier in the semester too, but when we created this stack frame, worth remembering because it doesn't come up too often. When we create this stack frame, we never put a stack frame inside another stack frame. The tracing tool can't even do that, so you can't make this mistake anymore. On pen and paper, we used to see this all the time. A stack frame can't go inside another stack frame. Stack frames are isolated environments on the stack. Can't have them inside other stack frames. But code blocks, we have a code block inside a code block inside a stack frame. Code blocks can nest as much as we want them to. Okay, this returns false. So the block for this conditional is never executed. Location is not incremented. That's the end of this loop because we got to the end of output. And then we're going to add at index 0 the value 6. So we add 6 there, and then 1 gets shoved down. Then we do the same thing for the value 5. We're going to compare 6 greater than 5, true. So we increment location by 1. We got location up by 1. And then does 1 come before 5? False. So we don't increment location again. So we have location 1, value to insert 5. At index 1, insert 5, and move 1 down the line. The loops end. The stack frame ends. We return a reference to that new output, that new array list, and then print it to the screen.